Here we are back at our kitchen sink lab. Just a little health and safety aspect. When it's a lab, no food and drink, you know, and when it's a kitchen, no lab stuff. Here we go. Okay, so we're looking at sensitivity and range and getting a standard reference point that is both consistent and conserved. Well, the way to do it is you put your containers in the same location and then mark off on a piece of paper. So I've got it here, I've got a straw of paper, or on the straw, and you can see this one here. This is marked off here on the straw. This is marked off here on the pieces of paper, okay? And then place them in some areas that we think are local, customary, and available to us that might give us some temporary measure of scale. So this is linear, so what I did here is I got a little piece of paper, my nice sharp pencil, and I used my linear scale, you know, the decimalised metre, and I marked off in 5 millimetre lengths, just temporarily, just to give me something to reference against. And then place sellotape these on the tube, and then my first reference point, room temperature. Here we are, room temperature. And I mark R1, room temperature. And then the second one was R2 is the fridge, yeah? And then R3, the freezer. Don't put the water one in the freezer, just the alcohol ones. And don't leave the small ones in too long. Okay, long enough to get it down and settled. Okay, so how consistent and conserved are those results? Well, we can see that the R1 reference is pretty much very variable. Here's an example here, right at the top of this scale. Yeah, and of course the room is going to be variable. Yeah, it is going to be variable. And here, if we have a look here, we can see that R2 a little bit more consistent. Oh, there's R1, there's R2 in here, and we can see that not so variable. If we look at our freezer, R3 here, we can see there's quite a variation if I try and do it. So it's not as consistent when I come back to it, and nor is it so conserved. Okay, we've been trying to set some sort of scale with our homemade thermometer. We've used the fridge, we've used the room temperature, we used a freezer. But if we look at our marks, there's quite a lot of imprecision, a lot of variation. What can we use to standardise that has consistency, that is each time we come back to measuring it, it will give us pretty much the same measure, and it's conserved? That is, it will hold that same measure without fluctuation while we're measuring. Perhaps we can use something else that is conserved and is consistent, and that is our own body temperature. So why not get in a sleeping bag, put on a good movie on a bad rainy day, tuck that thermometer under your armpit and watch a favourite movie. A really good one to watch is Ratatouille. You know that expression? Anyone can be a cook? Wow, anyone can be a scientist too. So, hold it there. You're going to have to hold it there for an hour or two until the temperature gets to your body temperature, and you want to do it a couple of times, and just mark it off when you get there, mark it off and see how consistent that is and how conserved that is as our standardised reference point for our scale of temperature. We call this one RO, okay, so we come up here and we can see RO here. We see very, very minor variations at different times with 2 different measurements here, so it's pretty consistent. We've decided upon R0, our standard reference point, which is the most consistent, most conserved, and allows for the most sensitivity for an instrument to be our human body temperature between 4 p.m. and 6 p.m. when we're not sick. You know, obviously when we're sick and ill, our temperature varies in response to that. Now we decide the top and bottom of our scale. So this is our top point, okay, reference point. We're going to make that 100. We decide. And we can, the number of divisions we're going to have between that and our bottom point, which is our freezer, yeah, is going to be 100 divisions between that. So our freezer will be 0 and RO body will be 100. That's our scale. We're going to call it the Humbod scale, the human body scale. It's fine. I mean, there's lots of different scales, there's lots of different names, you know, Celsius, we've mentioned already, you know, 100 boiling water, freezing, Fahrenheit. Another really, really important one in science is the Kelvin scale, yeah, where we take the temperature of 0, where all molecular motion ceases. And we'll talk about that later. What I've done is then converted for my thermometers so that we have a consistent scale. We have 100 divisions between RO and R3, reference 1 and 3. And it turned out that when I looked at it, Kevin, this little thermometer here, had pretty much, when I measured it, between R3 and R0, 100 millimetres. And that was easy for me. So therefore, our 100 divisions means that each of our divisions, each of our Humbod degrees, is 1 millimetre on Kelvin scale. But it doesn't work out that way for Kelvin. If I measured Kelvin between R3 and R0, when I first did it, I came up with 120. So we take the length in millimetres and divide it by the number of divisions that we want. The length in millimetres between our RO reference and our low reference R3 freezer, and divide that by the number of divisions, 100. 120 divided by 100 gives us 1.2 millimetres per Humbod degree or division, which means 12 millimetres per 10 degrees. Each 12 millimetres was 10 degrees. Mark the degrees are Humbod degrees. And then I did the same for Karina. When I measured Karina, of course, she didn't get down to the freezer because that would have frozen it. That thermometer, we had R2, which is the fridge. I came back to Kevin and Carl, and once I'd put their scales on, I marked off on the scale, on the Humbod scale, what the R2 was, the fridge, and it turns out it's about 35 on our Humbod scale. So what would 35 be on the Karina scale is the R2, and that's where that scale starts. And of course the R0, our body reference, is the 100. Again, I had to measure that. So if it's 35 to 100, that's 65 divisions for our scale, 65 Humbod degrees. How far was it? Well, it turned out it was actually 63 millimetres on Karina. If I wanted to be precise, I'd take the millimetres, divide by the number of divisions we wanted, 63 divided by 65, and that would give me, but 63 and 65 are so close, I just decided to go with 1 millimetre division per Humbod degree. For example, if it had been 130 millimetres and I needed 65 divisions, 130 divided by 65 would have been 2 millimetres, so each 2 millimetres would have been a Humbod degree. You can work it out. And I've colour coded it too, yeah? So this is our Carl one, and I've just marked in RO, which is our 100, our standard reference, the body temperature, R2, in this case it's 35, but our bottom one, R3, the freezer, 0. I've colour coded just so it's quicker and easier to just get an idea of where the temperature is. And I've marked my scale from 120 to -10 on the Humbod scale. And this is Karina's we scale, and you see we only go down to R2, which is the fridge, and R0, which we already have, our consistent and conserved standard reference point.
We've now completed 3 excellent little thermometers that operate on the Humboldt scale, and we are ready to start designing and carrying out our investigation using our new instrument.